In this video, we're going to talk about one last matrix operation that really deserves its own video. This is called the inverse of a matrix. So first off, we have the definition. If you have a matrix A, the inverse, which we will write here as A to the negative 1 power, is a matrix such that if you multiply A times A inverse, you get back to the identity matrix, and it doesn't actually matter which order you multiply them in. Now it says a matrix is called invertible if it has an inverse, and this is important in that not all matrices are going to have an inverse. We are actually going to see something later on that will tell us when we are guaranteed to have an inverse. In fact, we're going to have something called the invertible matrix theorem, which will give you a whole bunch of conditions that all are needed in order to have an inverse. With that said, a lot of matrices do have inverses, and so this is something you definitely want to be able to find. Before we get into the process of finding it, just look at a couple of quick properties here. If you take the inverse of a matrix, and then you take the inverse of that, you get back to the matrix you started with. And this is kind of an interesting one here, is when if you multiply two matrices and then take the inverse, you do get the product of the inverse matrices. However, it does switch the order on them. And if you want to check that, you can kind of just see here, if you take the matrix AB and you multiply by the matrix B inverse A inverse, then first off, you group together the middle two terms. B times B inverse is going to give you I. And then I, right, is the identity, doesn't do anything here. And then lastly, AA inverse is I. So we do get the identity there. That means this is in fact the inverse of the AB matrix. And now the big question is, how do we actually find this inverse? Now there is a shortcut for 2 by 2 matrices. I'm not going to go over it in this video, but if someone is interested, they can look in the book to find the shortcut. I'm going to show you the general process here. It's kind of a pain. So the idea is you write down your matrix, but you want to leave yourself some room on the right side because you're going to write in your identity matrix here. And then what you're going to do is you're going to do row operations until you get the row echelon form here, the ones and zeros on the left side. So we can do that here. I want to do -1 row 1 plus row 2 goes to row 2, and -2 row 1 plus row 3 goes to row 3. And let's see what we get here. The first row is not going to change this time. -1 is going to go 0, -2 is -4, -3 plus 4 is 1, -1, 1, 0. Then we're going to look at the next one here. We have -2 plus 2 is 0, -4 plus 7 is 3, -6 plus 5 is -1, and then -2, 0, 1. Now, I need to get a 1 in this spot here. Dividing by 4 would cause us to get a fraction in that row, multiple fractions to be honest. I don't have a 1 below it that I can swap rows here, but there is something a little clever I can do here. I'm going to go ahead and add row 3 into row 2 first. And what you see what's going to happen here is I have 3 plus -4 is -1, and -1, 1, 0, and then -2, -1 is -3, and we get this here. And then all I have to do now is multiply row 2 by -1, and that will get me the 1 that I wanted there, and I can avoid fractions this way. Now, you didn't have to follow this exact same steps that I'm doing here. You could have used fractions. There's nothing wrong with that. It's just a bit more of a pain here. Regardless, we get a 1 in that spot. And then we know we want to get a 0 below it. So I would do -3 row 2 plus row 3 goes to row 3. 0, negative 1, 1, 3. So negative 3 times 3 is negative 9, plus 2 is negative 11. And then 0, negative 1. Negative 3 times negative 1 is 3, plus 0 is 3. And then zeros don't do anything there. Then I need to get a 1 in this spot right here, this diagonal element. So I'll just do negative 1, row 3 goes to row 3. 3, 11, 0, negative 1, negative 3, 0, 0, negative 1. And then we're going to go ahead and get 0 above that. Just a couple more steps here. Negative 3, row 3 plus row 1 goes to row 1. 0, 0, 1. So negative 3 times 11 is negative 33, plus 1 is negative 32. Negative 3 is positive 9, positive 3. And then we have 3, negative 1, 0. 11, negative 3, negative 1. And one last step here to get rid of this. Negative 2, row 3 plus row 2. Sorry, plus row... messed up on that one. Negative 2, row 2 plus row 1 goes to row 1. And then 0, 1, 0, 0, 0, 1. So negative 2 times 3 is negative 6, is negative 38. 11. Negative 2 is positive 2, is 11. Negative 2 is 0, it's going to give me 3, 0, negative 1. And then once you get to this point, once you get the identity on the left-hand side, then the matrix here at the end, that is your inverse matrix. So again, if I write it out in detail up here, A inverse is the matrix negative 38, 3, 11, 11, negative 1, negative 3, 9, 0, negative 1. You can double check by multiplying and seeing if it does give you the identity or not. Also, in general, the process here is definitely long and painful. Calculators can be used to shorten it or to check your answer at the very least, but it's important just to understand the concept here of how we find an inverse and what does it actually do in a problem.